Okay, we are continuing example 16.3, where we are designing a timber beam. It's actually a joist, a part of a joist system. And at the end of the last video, we had decided to go with a 2x12, which has a section modulus of 31.6 inches to the third. We calculated the self-weight, or looked up the self-weight, calculated the moment caused by that self-weight, and then determined how many additional inches to the third of section modulus we need. It was a very small amount, only 1.8. When added to the initial requirement, resulted in a total of 30, which still is less than what we have provided. So this 2x12 will be adequately strong enough to resist the load without exceeding the maximum allowable bending stress. But when we're designing a beam, we also need to take into consideration deflection and also shear stress. Shear rarely controls, but something that needs to be checked anyways. First, let's check deflection. Deflection is much more likely to occur. So we have a simply supported beam with a uniformly distributed load. So the formula from Appendix H for the deflection is 5WL to the fourth over 384 EI. So I like to rearrange this formula for I. So I is equal to 5WL to the fourth over 384 E delta, and then calculate the I that is required and see if the beam that we have chosen provides that amount of moment of inertia. So it's going to be 5 times W. So what is our W? Well, let's go back up here and find in our previous calculations. By the way, we are only looking at live load deflection in this particular example. So that's not uncommon in structural design to only be concerned with the live load deflection. Because as I said, live load is stuff that moves around, like people who walk through a building impose a live load on the structure. And so we want to limit the live load deflection because that's what's going to essentially make the floor bounce or move or deflect while it's in use. The dead load deflection, what dead load tends to do is it tends to make a beam sag, but then because that dead load is always present, that sagging or deflection occurs initially upon construction, and then it just stays there. Whereas the live load, because it's coming and going, it's transient. It causes perhaps some motion in the floor, which we want to avoid in this case. So we're just looking at the live load deflection, which is 53.3 pounds per foot. I'm trying to see if we had already converted that to pounds per inch. It doesn't look like we have. So let's take that 53.3 pounds per foot. I'll come down here, 53.3 pounds per foot. This is our live load. It's just our live load. And we're going to multiply that for every 1 foot. There are 12 inches. So divide 53.3 by 12, and I'm getting 4.44 pounds per inch. So I'll put that into the equation up here, 4.44 pounds per inch. The length was 16 feet, the span length, but I'm going to want to convert that into inches. The reason for that is because modulus of elasticity will be given in PSI or KSI. The amount of deflection is in inches, so it just makes sense to convert these units up here into inches. Alternatively, we could convert modulus of elasticity and deflection into feet, but that just doesn't quite make as much sense, or at least it doesn't to me. I think it's easier to convert these linear units up top. So, so again, we've got 16 feet is the span length. So for every 1 foot, there are 12 inches. So 16 times 12 is 192 inches. That's our span length. So 192 inches. Don't forget to take that to the 4th power. Okay, it's real easy to accidentally forget about exponents. Over 384 times E. Now we had looked up E earlier. I think I wrote it down. Yep, it's 1400 KSI or 1,400,000 PSI. Since I've got pounds up here, let's go with the PSI value. So that's 1,400,000 PSI. It's the modulus of elasticity of hem fur. And deflection. We'll have to go back to the original problem statement to see what the allowable deflection was. And it says that we want to limit deflection to L over 360. So if our length is 192 inches, and we divide that by 360, that equals 0.533 inches. That's the maximum amount of deflection we want to allow. 0.533 inches. So units are real important here. That's the most common mistake I see. So just make sure we've got pounds and pounds. That's good. We've got inches, inches, inches. That's all going to cancel out. So I just need to simplify this expression, and we get 105.3 inches to the 4th. That's how big I needs to be. So we chose a 2 by 12. So I don't think we wrote down what the moment of inertia was. Let's look that up right now. It is 178 inches to the 4th. That's the moment of inertia we are providing with our 2 by 12. That's greater than the demand. We need to have at least 105.3 inches to the 4th, so the beam we chose is greater than 105.3. Therefore, it is okay. So we've just checked deflection. It's good. There's one last thing left to check, and that is shear. So let's check shear. We have, again, a simply supported beam with a uniformly distributed load. So the actual maximum amount of shear that this beam is going to experience is WL over 2. So our total W is 73.3 pounds per foot, plus the self-weight of the 2 by 12, which we chose, which has a weight of 4.68 pounds per foot. So those two things added together will be the total distributed load multiplied by a span length of 16 feet, and then divide all that by the 2 supports, and we get a maximum amount of shear of 624 pounds. So that's the maximum amount of shear that will be occurring at either end of this beam. So how much shear force can this chosen beam resist? Well, if you go back to our chapter where we talked about shear, we had the formula for a rectangular cross section, that the shear stress is equal to 3 over 2 the shear force divided by area. or 3 over 2 is 1.5. So we could write that as 1.5 V over A. So what we would like to do is we could check to see, since we we can look up an allowable shear stress, we would like to calculate what area is required. So we're just going to solve this equation for A rather than for F. And we get the required area is 1.5 times the total amount of shear divided by the allowable shear stress. So that's going to be 1.5 times 624 divided by the allowable shear stress, which we wrote down earlier. Right up here, it was 150 pounds, or I'm sorry, 150 psi. So 150 psi. So I've got pounds and pounds. Got to always check those units and make sure that they will cancel out. And so it's going to give me a required area of 6.24 square inches. So this is how much area we need. How much area do we actually have? So you don't want to just simply multiply 2 by 12. That is not our area, because the width of a dimensional piece of lumber is not 2 inches. It's actually only 1.5. And the height is not 12. It's actually only 11 and a quarter. So we could calculate this area using these dressed dimensions, as they're called, the actual dimensions. Or we can just simply look up in the appendix the area that's already tabulated for us. A 2 by 12 has an area of 16.9 square inches. So 16.9 is much greater than 6.24. So shear is okay. So we have checked bending stress, it's good. We've checked deflection, it's good. We've checked shear force or shear stress, it's good. So this seems to be a good beam, a good selection. A 2 by 12 will work. With timber construction, though, there's one last thing that can be checked, and that is the bearing stress. So at the end of the truss, it's going to be resting on top of something. Maybe it's resting on top of a plate, another piece of lumber laying on its side, or maybe it's resting on a steel girder or something like that. At any rate, there is an area here. There's a bearing area. And because wood is relatively weak in this compression perpendicular to the grain, this area is potentially of concern. We need to make sure it's large enough so that the load is spread out and does not exceed the maximum allowable bearing stress. So I'm just about out of time on this video. I will wrap up this example problem and double check our bearing area in the next video.